Welcome back, Math1720. Rolling through Chapter 5. We're going to be here in Section 5. We're going to do the double angle identities. Alright, be able to apply them, and then we're going to do product to sum. I'm not going to go through the proofs per se for all of these. I'm just going to go ahead and give you the double angle identities, and then I want you to be able to apply them when necessary. So these are the double angle identities. You need to write down each one so that it's on your trig identity sheet. So we have cosine of 2a. 2a, that's the double angle, right? 2 times whatever angle a is. Okay, we can rewrite cosine of 2a as cosine squared a minus sine squared a. We can also rewrite cosine of 2a as 1 minus 2 sine squared a. We can also use cosine of 2a as 2 cosine squared a minus 1. 3 versions for cosine of 2a. Alright, sine of 2a we can rewrite as 2 sine a cosine a. And then tangent of 2a we can rewrite as 2 tangent of a divided by 1 minus tangent squared of a. Alright, so, which version do you use? Well, it just kind of depends on the application. And you'll see as we do some example problems, why we choose, the first version, the second version, or the third version of cosine of 2a. But just remember, it's 2a, so that is why it's called the double angle. Twice the angle, right? So let's go through an example here. We want to find function values of 2 theta given information strictly about theta. Okay? So we're given cosine of theta equals 3/5. And we are defining that sine has to be what? Less than 0. That means sine has to be negative. So we have to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So what we have to do is we're only given the cosine of theta. We have to find the sine value for all of these. Okay? And it's restricting sine to being less than 0. So sine is negative, and our restrictions are when cosine is positive, that's in the 4th quadrant, and sine is negative in the 3rd and 4th quadrant, but it has to be when cosine, ends up positive. Remember, all students take calculus, so that's why cosine's positive in the 4th quadrant. So that's the quadrant that we're going to be looking into. Given cosine is 3/5, draw yourself a triangle, and you'll be able to get the sine value based on that. We should know, though, since it's cosine of 3/5, that 5 is the hypotenuse, we should recognize that this is a 3, 4, 5 triangle. Alright, so when we get this, our sine theta should equal, what, 4/5, but it should be negative 4/5, okay, because sine has to be less than 0. So, to find sine of 2 theta, alright, we have to find what sine of theta is. And I just explained that to you using the triangle, but we can also find it using the Pythagorean identity, right? Sine squared theta plus cosine squared theta equals 1. So this is just another way of finding the sine of theta, not sine of 2 theta, just sine of theta, because we're missing theta, right? But just practicing it, right? Using the Pythagorean identity, so we get 16 over 25. If we simplify that down, right? Because 3 squared over 5, that's 9/25. And then 1 minus 9/25. Alright, rewrite 1 as 25 over 25. So you're going to have 25 minus 9, which is 16 over 25. Alright, then we square root both sides, plus or minus the square root of 4/5. And obviously we want to choose the sign that is negative because that's the restriction in the problem, where sine of theta has to be less than 0. Alright, so now we know that sine is 4/5, or negative 4/5. I've told you 2 different ways to do it. Alright, we're going to use the double angle identity for sine. So we know that sine of 2 theta is 2 sine theta cosine of theta. So that's going to be equal to 2 times, we're going to replace sine of theta with negative 4/5, and we're going to replace cosine of theta with 3/5. So 2 times negative 4/5 times 3/5 ends up being negative 24/25. Okay. We're going to find cosine. Okay, we can use any one of the 3 forms for this one. It doesn't matter. Alright, we know the sine value and we know the cosine value. So this one's fairly easy. So we're going to use cosine of 2 theta equals cosine squared theta minus sine squared theta. So we're going to take 3/5 and square it and get 9/25, and we're going to take the negative 4/5 and square it and get 16/25. We're going to find the difference. All right, so cosine of 2 theta is negative 7/25. All right, there's a couple different ways we can use tangent. We know that tangent of theta, right, using the double angle identity, is just going to be sine of theta over cosine of theta. All right, so we can use those values. We can use the tangent theta equation, right, for the double angle that we're just going to substitute into. So the best way probably is taking sine of theta over cosine of theta. So when we work that out, we have negative 4/5 divided by 3/5. We're going to multiply the numerator and the denominator by 5/3, all right, because of our rules of fractions. The 5's will cancel, and we will be left with negative 4/3. Remember, that's tangent of theta, not tangent of 2 theta. We want to find tangent of 2 theta, so we're going to substitute into the identity. Remember, the identity tangent of 2 theta is equal to 2 tangent of theta divided by 1 minus tangent squared of theta. And we just substitute in our values. We now know that tangent of theta is negative 4/3. So in the numerator, it's going to be 2 times negative 4/3 divided by 1 minus negative 4/3 squared. Simplify, the fractions. All right, in the most simplest form, tangent of theta is going to be 24/7, or tangent of 2 theta. Okay? So we can take the quotient of 2 theta and cosine of 2 theta as well. That's an alternate way of finding tangent of 2 theta, because we found those before. We found sine of 2 theta, we found cosine of 2 theta. Okay, we can still use the identity of tangent is sine over cosine, right? But in this case, it's tangent of 2 theta is equal to sine of 2 theta over cosine of 2 theta. So we can take the double angle values that we found before, all right, which is negative 24/25 divided by negative 7/25, and we still end up with 24/7. So there are a lot of different ways to work through these problems. All right, get the way that is most comfortable with you. I'm not going to force you and say that you have to solve it in a specific manner. All right, find whichever one works for you for each problem. All right, let's look at example 2 here. We want to find the values of the 6 trig functions of theta given, right, cosine of 2 theta is 4/5. And theta has to lie between 90 and 180 degrees. So what's that tell me? We're looking for all the values in the second quadrant. Okay, that's where where theta resides between 90 and 180 degrees. So now we got to work backwards. We have the ratio 4/5, right? That's what sine of 2 theta is equivalent to. So we have to find a way to work backwards and relate everything. Okay, so we are going to say cosine of 2 theta is equal to 1 minus 2 sine squared theta, and we're going to substitute in the 4/5 for 2 theta. Why are we doing that? Because we want to find a sine of theta. Then once we know a sine of theta, we can find what cosine of theta, tangent of theta is in all the reciprocal identities. But choose one that's simplest to solve. All right, we chose this one because it just has the sine involved with it. Okay, so we're going to replace and solve for theta. So when we do that, all right, we're going to subtract 1 from both sides and then divide by negative 2. When we do that, we get 1/10 equals sine squared theta. Then we square root both sides, okay? When you square root both sides, you're going to get plus or minus square root of 1/10. Then we have to rationalize the denominator, all right? And since sine is in the second quadrant, it's positive, we're going with the positive version. So sine of theta is square root of 10 over 10. Now that we know that sine of theta is square root of 10 over 10, we can draw the triangle in that quadrant, all right, and find all the missing values. All right, so now that we know the hypotenuse is square root of 10, okay, we can work backwards. All right, and it's easier to work backwards. I'm going to step back a slide. If we use the square root of 1 over the square root of 10, or 1 over the square root of 10 when we draw the triangle, We don't necessarily need, we always rationalize the denominator for our final answer. So square root of 10 over 10 is what sine of theta is equal to. But we want to use 1 over the square root of 10, so before we rationalize it, to actually draw the triangle to get the other values. So we can see when we can do this, we use the Pythagorean theorem to find the x value. It ends up being -3. So now we're able to see that, okay, cosine of theta is what? Adjacent over hypotenuse. This is all, chapter 1 stuff from here. Cosine of theta is -3 over square root of 10. Rationalize the denominator, so cosine of theta is 3 square roots of 10 over 10. So this is nothing new right here whatsoever. Tangent's opposite over adjacent. Okay, cotangent, we can just take the reciprocal of tangent. All right, same with secant, take the reciprocal of cosine, and cosecant, take the reciprocal of the sine value. So that's all nothing new to you guys. That's all stuff we've been doing all semester long. So no new calculations or anything there. All right, next step here. All right, we want to verify the trig identity. So we want to verify that cotangent of x sine of 2x is equal to 1 plus cosine of 2x. We want to verify that it's an identity. All right, so remember when we choose these, we always pick the more complicated side. The more complicated side is cotangent of x sine of 2x, right? Because 1 plus cosine 2x is an identity that we're trying to find. So we can rewrite cotangent of x as cosine of x over sine of x. Okay, be very, very careful here. That sine of 2x and sine of x do not cancel, all right, because of the double angle. So the sine cannot go away yet. So we have to rewrite sine of 2x in terms of just sine and cosine. So pick the right double angle identity that helps you simplify. So don't cancel that sine of x in the denominator with the sine of 2x. You have to rewrite the sine of 2x first. So we're keeping cosine of x over sine of x. Now we're going to rewrite sine of 2x as 2 sine x cosine x. Now the sines can cancel. All right. So now the sines cancel. We have cosine of x times cosine of x, which is cosine squared of x. And we have the 2 out in front. And when you rewrite 2 cosine squared of x, all right, it becomes 1 plus cosine of 2x. All right. We can do that because the original identity is cosine of 2x is equal to 2 cosine squared x minus 1. When we rewrite that and solve, all right, for 2 cosine squared of x, all right, algebraically, when we solve that, right, we can add 1 to both sides and then manipulate over the cosine of 2x. All right, we end up with 2 cosine squared of x, and then we can replace it. Okay, so just solving one of the identities for a missing piece. All right, let's simplify each expression now. So we have cosine squared of 7x minus sine squared of 7x. Okay, so we're going to use our double angles here. So why, how's that a double angle? 7x is our angle in question, right? So if we use double angles here, we can rewrite this as saying, all right, we have cosine of 2 times 7x. Okay, that's our angle. We're using our double angle identity here. Okay, so the problem has a cosine squared of 7x minus sine squared of 7x. That's an identity. That's equal, the identity's in the blue on the right. Okay, so if you look at your trig identity sheet, you should see that you have cosine of 2a is equal to cosine squared of a minus sine squared of a. Okay, a is 7x in this case. So now we can simplify this down. So we're going to rewrite this. The cosine squared of 7x minus sine squared of 7x is equal to cosine of 2 times 7x. So remember, 7x is our a in this case. So we end up getting cosine of 14x. So that's about as simple as we can get on that one. All right. Now on example B, we have sine of 15 degrees, cosine of 15 degrees. Okay, obviously we have, so this is like a sine A, cosine A. When we take a look at this, all right, the way to work out of this one is we need to multiply by 1. And we're going to multiply by 1 in the form of 2 over 2, or we can consider it 1/2 times 2. Either or gives us a 1. Why do we need to do that? So that we have the 2 out in front. so that we can apply the double angle here. So we can rewrite this as 1/2 times the quantity of 2 sine of 15 cosine of 15. And when we do that, we can rewrite that using the identity. We have sine of 2a is equal to 2 sine a cosine a, right? That's our identity. That should be on your identity sheet. Okay, we want to be able to apply that now. And that's the whole reason we multiply by 1, is so that we have the 2 in front, so that we can use, the other side of the double angle. So when we do this, we end up with equaling 1/2 sine of 30 degrees. Okay, we can also fix that, right? We know sine of 30 is equal to 1/2. So we get 1/2 times 1/2 was equal to 40. Or 40. 1/4. Sorry about that. Alright. Next example. We want to write sine of 3x in terms of sine of x. So we're not quite at a double angle theorem here. We have to rewrite, okay, what's in the parentheses. Remember, we call that the argument. So we're going to take sine of 3x and we're going to rewrite sine of 3x. How are we going to rewrite that? We're going to rewrite the argument as sine of 2x plus x. Okay, so we can see that there. Now we can rewrite some things. Okay, now our argument is 2x plus x. That's sine of what? A plus b. So that's from before. Okay, that's from a few lectures ago where we had sine of a plus b. Alright, so that's our sine sum identity. So you can rewrite that as sine of a cosine of b plus cosine of a sine of b. If you guys remember doing that, look at your trig identity sheet, it's on there. Alright, so when we rewrite this, we rewrite it as sine of 2x cosine of x plus cosine of 2x sine of x. Now we have double angles. Okay, we have sine of 2x and we have cosine of 2x in this problem. We can rewrite using double angle identities. Okay, so we rewrite sine of 2x as 2 sine x cosine x, and then we rewrite the cosine of 2x as cosine squared x minus sine x, or cosine squared x minus sine squared x. Alright, and that'll all be times sine of x there. Now, distribute through. Alright, when we distribute that cosine of x through, we end up with 2 sine x cosine squared x plus cosine squared x sine of x minus sine cubed of x. Okay, so important for us is seeing how we can simplify this down. Like, it looks really complicated right now, but we can break this down by doing some factoring. Very, very important for us, factoring and some rewriting. Always look to factor or rewrite. In this case, we're going to rewrite. So we have 2 sine of x. We're going to rewrite cosine squared x all in terms of sine squared x. That's just us rewriting the Pythagorean identity. So cosine squared of x becomes 1 minus sine squared x. That's rewriting the Pythagorean identity. Plus, we replace the other cosine squared x with 1 minus sine squared x. Okay? Now, we can distribute through. Everything is all going to be in terms of sine. That's the only reason we did all this. Because the problem asks us if we take that piece and write it only in terms of sine x. So we're in the left-hand side of the equation, all right, we're going to distribute 2 sine x to the 1 and to the minus sine squared x. When we do that, we get 2 sine of x minus 2 sine cubed of x. And then we're going to distribute the sine through on the other side, so we end up with sine of x minus sine cubed of x minus sine cubed of x. Then we just combine like terms and simplify everything down as far as we possibly can. Okay? Alright, example 6, real world problem. Okay, if a toaster is plugged into a common household outlet, the wattage consumed is not constant. Instead, it varies at a high frequency according to this model. Okay, we have W equal V squared over R. Okay, well, voltage squared divided by R. Okay, that's our power. And we call it, power is measured in watts. So that's why the W is there, okay? Normally it's work, but in our case, okay, the W is for watts is voltage squared over R. So that's how we actually calculate power. So the voltage is the voltage that you plug into the wall. Okay, there's an equation for voltage, and then the toaster has a certain amount of resistors, and those resistors give off heat, and that's what toasts your toast. Kind of like defrosting your car window. In the back, those little lines that you see across your window, all right, those are just long resistors, and you turn them on, and they heat up and they give off heat, and that's how you defrost your windows. Okay, so the graph, okay, we can take a look at wattage consumed by a typical toaster. We're going to assume that resistance is 15 ohms, and the equation for voltage is 163 sine of 120 pi t. Okay, so we can graph that in your calculator and take a look at in the viewing window, 0, 0.05. So that's your x minimum, okay, y minimum, and then you have, or sorry, max, right, and then you have your other x and y. So those are your windows that you're changing for this. Okay, we want to calculate the oscillations. Okay, so when we take a look at this, all right, and we substitute this into the equation here, you can just hit y equals on your calculator and plug in the voltage equation. Don't forget to square it. Okay, the voltage is 163 sine of 120 pi t, but it's voltage squared to get power. When you're plugging this into your calculator, remember you can't use t in your calculator, you need to use x, all right, and then divided by 15. So we can take a look and count the number of oscillations there. All right, so we have our x min is 0, our x max is 0.05, and then our y min is -500, y max is 2000. All right, and we're able to take a look and count the oscillation. So in this case, all right, I just count the, you can count the peaks of the voltage if you want to, but if you count, there are 6 peaks. All right, so the graph shows that there are 6 oscillations. All right, next we're going to get into half angle identities, all right, and product to sum identities and where those come from. All right, so we're going to go product to sum for cosines. All right, and then I'm not going to spend a lot of time on the proof piece. I just want to get to the examples. But we can go product to sum if we multiply these out and where we're going to get. So I'm just going to kind of cruise through the product to sum, all right, so that we can kind of see what they come out to be. Okay, so when we write this, we have our other identities. So we can say the sine of a plus b, okay, is essentially what we've used before. We've done the difference identities before, and we can obtain all the product to sum identities. So for us, don't worry about writing any of this down yet. The next slide is going to tell us everything that I need you to write down. I just kind of want to cruise. There's kind of where they come from, how they're applied. These are the identities that you need to write down. So these will be on your trig identity sheet. These are the product to sum identities. So we're doing what? We're multiplying, all right, and they equivalent to an addition, okay, with the angles. I don't expect you to memorize all these because there's a lot to them. All right, so if we have cosine of A times cosine of B, that's going to be 1/2 cosine of A plus B plus cosine of A minus B. If we have sine of A sine of B, that's going to be 1/2 cosine of A minus B plus cosine of A plus B. If we have sine of A cosine of B, we have 1/2 sine of A plus B plus sine of A minus B. And lastly, we have cosine of A sine of B, that's going to equal 1/2 sine of A plus B minus sine of A minus B. So just make sure that you pause the video, get all those written down on your trig identity sheets. So let's do an example here. All right, so we write, okay, 4 cosine of 75 sine of 25 as a sum or a difference of 2 functions. All right, so we're just going to go ahead and rewrite that. Keep that 4 out in front. It's just a scalar, it's just a multiplier. All right, so when you rewrite using the identities, keep the 4 in front, and then we know that 75 is A, 25 is B. All right, and then we're just able to rewrite this. 4 times 1/2 sine of 75 plus 25 minus sine of 75 minus 25. We can reduce those, okay? So sine of 75 plus 25 becomes sine of 100. sine of 75 minus 25 becomes sine of 250. And remember that 4 divided by 2 is 2, and that 2 needs to distribute to each term. All right, it's not just in front of the first term. Okay. Now let's go the other way. We want to go sum to product identities. I'm not going to read through all these. Go ahead, pause the video. I'll write them all down, and then we'll just kind of go from there. It's literally just substituting in and solving and simplifying. So now we're going sum to product. Okay. So we want to write sine of 2 theta minus sine of 4 theta as a product of two functions. All right, so we got a difference here. So we're going to use the identities. Okay, we recognize that we have 2 theta is A and 4 theta is B. So when we rewrite that, we're going to end up with 2 cosine of 2 theta plus 4 theta divided by 2 times sine of 2 theta minus 4 theta divided by 2. Okay, we can rewrite those, right? 2 theta plus 4 theta is 6 theta, and 2 theta minus 4 theta is negative 2 theta. They're both divisible by 2. Okay, so we can simplify those down even more, right? 6 divided by 2 is 3, and 2 divided by 2 is 1. So this simplifies down to 2 cosine of 3 theta sine of negative theta. And last part of that, all right, we can use, we can turn sine of negative theta into sine of theta. All right, remember on our properties. Okay, so that one's on your sheet as well, and it becomes negative sine theta, but the negative we put out in front of the entire solution. All right, guys, so I know that that's a lot thrown at you, a lot of identities, but it's really just breaking down the given equation into what's A, what's B, and then looking at my trig identity sheet and applying it. It looks more complicated than it is, but you guys will have plenty of homework problems to practice doing this. Once again, just remember, shoot me an email if you have a question, or go ahead and remember to ask in class. Anyhow, I'll see most of you guys in class. Else the rest of you guys have a great day.